Okay, why did I tell you a bunch of abstract maths in the last video? It's because of a design pattern called reduce. Reduce is a general method for writing efficient computations that take a list of values for inputs and produce one single value for output. So let me remind you the definition of a monoid. It's in ask its data. Monoid A is a packet of data which contains a neutral element and then a function with two inputs. And we need to have three proofs, two that say that the neutral element actually is a neutral element. That is to say, if you use it as one of the inputs of this function, then it will return the other one unchanged. And then a third proof, which says that the two different ways of bracketing combining three inputs with two applications of this function are equal to each other. Okay, now let me write a definition of the reduce function in ask. So it's a function which will take a list of A's and produce a single A, and then as another input, it will take a monoid structure on A. So let me define it. I'm going to say inductively X's on the list. Now I'm going to say from M to unpack my monoid. So this allows me now to give a name to the neutral element, which I will call I, and the operator, which I will call F. And then I'm going to say from X's, and this will cause me to case split into whether this list is empty or not. Now, in the case when the list is empty, reduce is going to return the neutral element of the monoid, which is I. And when the list is head cons tail, what I'm going to do is I'm going to call the monoid operator F, where the first input is head and the second input is a recursive call to reduce tail. And then reduce needs to also be given a copy of the monoid. So this is a definition of reduce in ask. Now, I'm going to show you some things that you can do with this function and then afterwards explain a bit about how it works. So first, let's take the monoid for addition, which is a monoid on the natural numbers, whose neutral element is 0 and whose operator is plus. So remember now, at this point, I should write three proofs, two that say that 0 is the neutral element for each of the two inputs of plus, and then one for the rebracketing equation. Now, if I reduce using this monoid, I'm going to get a function which will take a list of natural numbers and returns a single natural number which adds them all up. So it's the sum operator on list. So it takes a list of natural numbers and returns a single natural number, which is their sum. And I can say define sum equals reduce addition. I've made a mistake. Oh yeah, I missed out my define here. Okay, so to show you that this works, let's say test sum, and I can make a list like 1 cons 2 cons 3 cons empty. So this should return 6, which is the sum of these numbers. And it does. Okay, what else can I do with it? Well, if I take the monoid of booleans with and true, so that's this one, make monoid true and if I reduce that, I get a function called all, which takes lists of booleans to booleans and will return true if every boolean in this list is true and false if at least one is false. So I can say define all equals reduce and. I made a mistake again. I keep missing out my defines. There we go. So this is useful in combination with the function map, which applies a function to every element of a list. So for example, I can write a function called even from natural numbers to booleans, which decides whether a natural number is even or not. So I can say define even n inductively n, and then define even n from n, and then define even 0. I'm going to return true because 0 is even, and then for successor case, I'm going to recursively call even on n-1 and then flip the result with not. So you can see how this function works. It counts down to 0, and every time it flips between true and false for even and odd. From n, what have I done wrong? I think that's the same thing I just wrote. Okay, I don't know what mistake I made. Now, if I take a list like this, 1 const 2 const 3 const empty, if I map even over it, this will replace every entry with either true or false, depending on whether that entry is even or odd. And then if I say all of that, this will decide whether every number in this list is true. So it will return true if they're all even and false if at least one is odd. So in this case, this should return false because we have a couple of odd numbers here. There we go. Now, in a small variation of this, if I take the or monoid, so it's instead of saying true with and, I say define or is make monoid false with or. So that's a different monoid on the booleans. And if I reduce this, I get a function which is sometimes called sum, which will decide whether at least one thing in this list of booleans is true. So it will return true if at least one is true and false if they're all false. So I can say define sum equals reduce or. So now if I do the same thing, but I change this all into sum, this will now decide whether at least one number in this list is even. So in this case, it should return true because it contains number 2. There we go. Okay, let me explain a bit about how this works. Remember that lists are built by starting from the empty list and then using cons to join elements onto the front one by one, working backwards. So let me just replace these with normal syntax to make it clearer. What reduce does is it will replace the empty list with your neutral element, and it will replace cons with your operator. So if we take, for example, the sum function, which is reducing addition, which has plus for its operator and 0 for its neutral element, if we sum this list, it's going to replace the empty list with 0, the neutral element, and it's going to replace cons with plus. So you can see that this sums the list, and then when it reaches the end, it does an extra +0, which doesn't do anything because 0 is the neutral element for plus. Okay, so let me say something about why reduce is important. It's because it can be implemented very efficiently on parallel hardware. So this is a particularly stupid implementation of reduce that does not go fast. But in a real programming language, there are implementations of reduce which will go fast. The important thing is that a monoid satisfies the rebracketing equation, which means that I can split this problem up any way I like. I can cut this list up recursively in any way into pieces like this, or alternatively, I could say it's like this or anything else like this, and I'm guaranteed to get the same answer. What this means is that you can write a generic load balancer, which will slice your list up as it chooses and give subproblems to different worker threads, possibly on different CPU cores. And the load balancer doesn't have to know anything about what your problem actually is. You can write something that works generically for any problem that looks like reducing a monoid. And then this is useful because many problems look like reducing a monoid. Okay, so in most serious programming languages, there are very fast implementations of this. Most famously, there is one which was used in-house by Google,